Welcome back to another video. So in today's video, we'll be explaining regarding VSEPR. So what does VSEPR stands for? It stands for valence shell electron pair repulsion. VSEPR theory states that two ideas, as the first one are saying bond pair and lone pair electron around the central atom arrange themselves to be far apart as possible to minimize repulsion. The second ones are the order of repulsion strength. Lone pair to lone pair are stronger than lone pair to bond pair, while the weakest one will be bond pair to bond pair. So the function of VSEPR theory is used to predict the geometry shape of molecules or even polyatomic ions. So let's start off with linear geometry with its notation AX2. The ideal bond angle is 180 degrees. For example, carbon dioxide, which contains two bonding pairs and no lone pair. Moving on, we have band geometry with its notation AX2E. The ideal bond angle is 104.5 degrees. For example, water which contains two bonding pairs and two lone pairs. Lone pairs take up space, then pushes the bonds closer to each other. Trigonal planar geometry, on the other hand, has a notation of AX3 with its ideal bond angle 120 degree. For example, boron trichloride, which contains of three bonding pairs and no lone pair. Here we have tetrahedral geometry with its notation AX4, an ideal bond angle of 109.5 degrees. For example, methane, which consists of four bonding pairs and no lone pair. Lastly, we have trigonal bipyramidal geometry with its notation AX5. There are two ideal bond angles for this particular geometry, which are 90 degree and 120 degrees. For example, phosphorus pentachloride, which contains five bonding pairs and no lone pairs.
I'm Lin Chen. So now I'll be sharing about how do you determine the VSEPR model.
First, we'll be starting by drawing Lewis structure.
Example on how do you determine the VSEPR of boron trifluoride, starting by counting the total number of valence electrons. Then the central atom must be the least electronegative. Then arrange the electron to achieve the minimum repulsion. After that, you can find there are three bonding pairs around the central atoms. Therefore, the geometry shape of boron trifluoride is trigonal planar. To sum up, VSEPR theory is like a blueprint for understanding molecular geometry. By knowing the numbers of bonding and lone pairs, we can predict shapes like linear, trigonal planar, tetrahedral, and band. And this knowledge helps us understand why molecules behave the way they do. Thanks for watching.